Hello everybody, welcome back to another geometry lesson. Today we're going to take a look at lesson 10.5, which is all about volume. Now, when we are talking about a volume of something, we are going up a dimension. What I mean is, we're going from 2D shapes into 3D shapes. A transition that can be a little bit scary for some people. But rest assured, according to many students, 3D is about the same level of difficulty as 2D. You just have to sometimes multiply by a height. So let's talk about what volume is, and then see what we can do with volume. When we talk about the volume of a solid, we're talking about how much space there is inside of it. The volume of a glass of water is how much water would fill the glass. The volume of a building is how much empty space there is in a building. When we talk about volume, we always talk about it in terms of cubic units. So the volume of a solid is the number of cubic units inside it. When we say cubic units, we mean things like inches cubed, or feet cubed, or millimeters cubed. We're essentially trying to see how many cubes of 1 inch, 1 foot, or 1 millimeter would fit inside of a shape. We're going to start by talking about the volume of a prism. And now, what is a prism? A prism, in plain English, is a box shape. This is an example of a prism. It's got some edges, some faces, and some vertices. So, the solids that make up a volume, such as this side of the box or this side of the box, are called the faces. The face is like the flat space. The edge of a polyhedron, which is another name for a 3D shape, is this, sort of the line that connects two faces together. Last, most certainly not least, a vertex is one of the corners of a polyhedron. So, when we talk about the volume of a prism, we're trying to basically see, okay, how much space in cubic inches or centimeters or whatever can fit inside of the box. The formula for the volume of a prism is much easier than it seems. The volume of a prism is volume equals BH. Not Bloomfield Hills, but base times height. B is the area of the base, and H is the height. Done. So based on the type of prism you're dealing with, just find the area of the bottom of the prism, multiply it by the height. Let me give you an example. If I gave you a shape here, I'm going to make it sort of a box shape. There we go. And I'm going to also draw the back of this shape, just so we can see. If we were able to have X-ray vision through this box, we would see these edges and faces. If I asked you to find the volume of this shape, you would first need to find the area of the square here. So we could use all of our regular area formulas to do that. Once you have the area of the base, B, all you have to do to finish off the problem is multiply it by the height of the prism. So let's say our base B, our height would just be this. Done. Let's take a look and see if we can do this with some of the examples in example 1. So at the bottom of the page, we've got example 1, and we have to find the volume of some of these solids. A prism is just a box shape, but I never said the box has to have a square as the bottom of it. A prism is any box that can be made from any shape base. So in example 1a, what shape is the base of the prism? Well, it's a triangle, and more than that, this right angle up here tells us it's a right triangle. If I wanted to redraw the base, which I recommend doing, it would look something like this. This is the base of our prism. But what measurements does it have? Well, in a prism, the top and bottom faces are always going to be identical. So if the top base has a short length of 3 centimeters, the short length of the bottom will be 3 centimeters. If the long measurement on top is 4, the long measurement on our base is 4. So to find the volume of this prism, we would just have to do the area of the base times the height. How do we find the base? Well, this is where we have to think of what shape it is and what formulas we can use for that shape. Since this shape is a right triangle, we know that the area of a triangle is 1/2 lowercase b h. In this case, the base of this small triangle is 4, and the height is 3, so the base would be 1/2 of 4 times 3. 1/2 of 4 times 3 is 6. So the area of the base is 6 centimeters squared. Plug this into our volume formula and we get volume equals, the area of our base is 6, the height of the prism is 2 centimeters. What's the volume of the prism? It would be 12 centimeters cubed, since, as a reminder, with volume, our units are always to the 3rd power, or cubed. This is how we can find the volume of a prism. Okay, what if you have a weird base? Something like in problem B. Same deal. Find the area of the base, multiply it by the height. So, let's identify what shape this is and see how we can find its area. Right away, we can see that this is not a square base. It's a trapezoid. The small base has a measurement of 6. The large base, according to the top of the problem, has a base of 14. And the height of this trapezoid is 3. So, in order to find the volume of the shape, volume equals base times height. We just need to know how to find the base. Instead of solving for the base over on this side, I'm probably going to plug it directly into my formula over here. It'll make it a little easier to deal with, so I can just do one calculation. The base is a trapezoid, and the area of a trapezoid, as we learned in Unit 7, is 1/2 base 1 plus base 2 times height. So I'm going to plug all of this in to my formula here. The volume will be 1/2 of, well, base 1 looks to be 14, so I'm going to put a 14 here. Base 2 looks to be 6, so I'm going to put a 6 here. The height of the trapezoid is 3, so this is going to be times 3. This part of our formula is just b. This is the base of the shape. The last thing we need to multiply is the height of the prism, and the height of the prism is 5. So the volume of this shape is going to be, if I wanted to do it in one calculation, which I do, 1/2 of 14 plus 6 times 3, that first part's the base, times the height of the prism, which is 5. Plug this into your calculator and see what you get. 14 plus 6 is 20. Half of that gives us 10. 10 times 3 gives us 30. 30 times 5 gives us 150 centimeters cubed. Very, very nice. Perfect. What I'm going to do now is I'm going to assign you a little bit of a video to watch. In the description of this video, there is a video that will describe Cavalieri's principle. It is a principle that is going to be very, very important going forward, but it's so difficult to describe here on this video that I need you to watch the video that's in the description. It's very brief, should only take a couple of minutes, and you can sort of skip through it once you get the idea, but I want you to pause this video, open the link in the description, and watch that video first, then come back. Stop here, and come back when you're done. Hopefully you've had a chance to take a look at that video so far. Again, if you haven't, you're going to be a little confused. But Cavalieri's principle is the principle the video shows that says it doesn't matter how you cut up or shift your shape, it's going to have the same volume as long as you don't change the cross-sectional area. The cross-sectional area being the area of each of those slices that was in the video. I apologize, you can tell I'm at the school because of the bell. But Cavalieri's principle states that if two solids have the same cross-sectional area, or same height and cross-sectional area, their volumes are equal. This means that no matter how slanted one of our prisms is, we can just solve it the same way we always have. Before we go forward, I want to talk about a special type of prism called a cylinder. So, the prism that we were talking about before is a box, right? It could be any sort of base. You can have a triangular base or a trapezoid base or just a box like this that has a rectangular base. A cylinder is just a prism that has a circular base. Kind of like this roll of tape here. The top of it is a circle, so that's the base. But if I look at it from the side, it's basically just a box. It's a 3D rectangle. Because of this, since a cylinder is just a special type of prism, the formula is also going to be the same. The volume of a cylinder is base times height. Now, we can get more specific, and usually on tests, such as the SAT, you'll see the formula written in a more specific manner. After all, if the base is a circle, does it need to be just written as base times height? Well, if your base is always a circle, then we could just write the area of a circle times h. The area of a circle is pi r squared. So the volume of a cylinder is pi r squared h. Very nice. You're going to oftentimes see me drawing a cylinder like this. Draw a circle up at the top. Draw some lines going straight down. Copy this part of the cylinder. This is if you don't want a cylinder you can see through. But if you want to see through the cylinder, I would also recommend dotting the top part of our first circle. That's a cylinder. So let's take a look at problems C and D. I want you to pause the video and see if you can find the volumes of these two shapes. Remember, with part D, Cavalieri's principle helps here. Pause the video and see what you can do. How did we do? As we can see here, a lot of my answers I wrote down in terms of pi, like 486 pi feet cubed. This is pretty standard when you're working with circles. You don't need to, you could always just write it as a decimal, but it makes the calculations a lot easier and a lot neater if you don't have decimals to worry about. With that said, if you have questions about these, let me know. Before we move on to the next page, I want to talk about two more quick things. We're dealing with the 3D world now, and with the 3D world, we start to deal a lot more in things that we can touch and actually interact with. One quality of things in our world is the quality known as density, how dense something is. Have you ever heard the saying, a kilogram of steel has the same mass as a kilogram of feathers? This is true. If you put them both on a scale, they're both a kilogram. But a kilogram of feathers, you would need a lot of feathers to make a kilogram, whereas a kilogram of steel is a pretty small piece of steel. This is because, even though they have the same mass, they have different densities. The density of an object is essentially how compact it is. Is all of its material really clumped close together, or is it spread out a little bit? Think about trying to put your hand through a block of Jell-O versus putting your hand through a brick. You can put your hand through a block of Jell-O just fine because it's not very dense. It's basically just gelatinous water. But a brick is far more dense. It's rock. So, again, density is a measure of how compact something is. In more scientific terms, it is the amount of matter inside an object per unit of volume. It's the amount of matter, the amount of stuff inside of an object per unit volume. What this means is we can actually write a formula here for density that we can use in math problems. Since the density is defined as matter per volume, we can literally write it as something's mass, which is usually going to be written in grams, that's the standard measure of mass, divided by its volume. More on this in a little bit. Before we talk more about density, and the fact that its measurement is usually going to be grams per something, like grams per centimeter cubed, I want to talk about similar solids now. For this demonstration, I'm going to draw two cylinders here. So give me a minute to draw those. Let's say I've got a cylinder here that's relatively short, and I've got a cylinder that looks very akin to it, looks just like it, but it's going to be a little bit bigger, like this. We might say this version just looks like a scaled up version of this. This is where we get into the idea of similar solids. In order for two solids to be similar, we know we have to be able to find a scale factor between them. Let's say that this is 5 and this is 10. Well, the scale factor of those two measurements, the radii, would be 5 times 2 equals 10. Our scale factor is 2. You can always divide the second by the first to also get your scale factor. In order for two solids to be fully similar, though, all of their linear measurements would have to have a scale factor of 2. 5 to 10 makes sense. The height of this cylinder is 1, the height of this cylinder would have to be 2. So that's the deal. All their linear measurements, like radii, or height, length, width, those would have to be similar in order for the shapes to be similar. In our definition, we can say exactly this. Two solids are similar. And again, this is the symbol for similar. If their linear measures follow equal ratios. If their scale factors are the same. The K for 5 to 10 is 2, the K for 1 to 2 is 2. But there is an asterisk here at the very end that I need us to focus on. When finding the volume cube your K value. That's right. If you're trying to use similar figures to find a volume, volume is a cubic measurement. So you will need to cube your scale factor. Looking at this cylinder here, I'll tell you right away, the volume is going to be 25 pi. If you don't believe me, you can try and solve it yourself. But with a radius of 5, this cylinder has a volume of 25 pi. If we wanted to find the volume of this cylinder, we have to take K cubed and multiply our volume by K cubed. If our scale factor was 2, we have to find what 2 cubed is. It's 8. So multiplying 25 pi by 8 would give us the volume of this cylinder, which 25 times 8 would be 200 pi. Again, if you don't believe me, calculate the volume of this cylinder. We know the formula for it. Be very careful with this, folks. When we're doing similar figures, cube your scale factor to find the volume. With that said, let's do these next couple examples. We're going to use the ideas of density and similarity to tackle the next two full examples. So let's consider the following. We're building a rectangular chest. We want the length to be 6 feet long and the width to be 4 feet. This is going to be a very, very large wooden chest. We want the volume to be 72 cubic feet. And the question's asking, what should the height be? This is a problem where we have a lot of information, but are also missing some information. Volume, after all, equals base times height. But it also works backwards. If you know, for instance, the volume and your height, you could find the base. If you know the volume and your base, you could find the height, just by plugging in the numbers. So here's how we would approach this problem. Start by finding the base of our wooden chest. Plug that and our volume of 72 in to the formula, then solve for h. So let's start by finding the base here. Since it's a rectangular chest, we know the base is going to be a rectangle. The area of a rectangle is just the rectangle's base times its height. If we're looking at the top of the chest or the bottom of the chest, the length is 6, the height is 4. 6 times 4 is 24 feet squared. So, we can plug it all into our formula. The volume is supposed to be 72, so we'll plug that in for V. The base, we just said, is 24, so we'll plug that in for B. All we need to do is solve for H. To do that, we can just divide both sides by 24. 72 divided by 24 gives us our height of 3. But 3 what? Well, volume is a cubic unit, but our height is just a distance. the distance is just going to be in feet, just like all the other measurements. So 3 feet tall. Very nice. Now we're going to talk about the density of this object. So here's a fun fact. The difference between objects that float on water and objects that sink in water mostly comes down to their density. Water has a density of 1 gram per cubic centimeter, which in the metric system, in imperial units, it might be 252.89 grams per cubic inch. If an object is more dense than water, it'll sink. But if an object's density is less than this density here, it will float. We want to see if our chest will float, but it's made out of a very heavy walnut wood. Walnut wood has a mass of 800 grams. Sorry, our chest has a mass of 800 grams. And we want to see if this chest will float. Recall, folks, that density equals mass over volume. So to find the density of our chest, we have to take its mass of 800 grams and divide it by its volume. But the volume of the chest is given. It's 72 feet cubed. The density of our chest is just going to be 800 over 72. 11.1111 repeating. But be careful of your units. Since we're doing grams divided by feet cubed, our unit is grams per feet cubed. If we're trying to compare this to the density of water, we will not have good luck. Why? Because the density that we're given is in inches cubed. So let's figure out how to convert this into inches cubed. To convert this into inches cubed, keep in mind that there are more inches in a foot. What this means is our bottom number, instead of doing 80 divided by 72, we could multiply by 80 divided by however many inches that is. So let's do that instead. 80 grams divided by, to convert feet into inches, multiply your number of feet times 12. And this will be inches cubed. So if we do 800 divided by 72 times 12, we get this, 0.93, which is way, way, way light. It's super light. In fact, it's so light that, or so, I should say, not dense, that if you tried pushing this under the water, it'd probably spring right back up. Our chest will absolutely float because 0.9 grams per inch cubed is way less than 252.89 grams per inch cubed. Very nice. Example 3 is going to be figuring out whether these two cylinders are similar. I'm going to open sort of a challenge to you, which is to try and find the volume on your own. Remember, our scale factor is going to come into play. So pause the video and see if you can find the volume of the new cylinder. Then we're going to walk through it when we come back. The first step to finding the volume of your new cylinder is to first figure out what the scale factor is between our linear measurements. Remember, to find the scale factor, find a linear measurement in the second cylinder and divide it by the first. Here we're given the radius on both of them, so we can just do 6 divided by 3. Our scale factor is 2, because 3 times 2 will give us 6. To use this scale factor to find the volume, though, we don't just multiply our volume by 2. It doesn't quite work like that. We need to use k cubed, or 2 to the third power, which is 8. So by multiplying 45 by 8, we will get the volume of cylinder B. Since 45 times 8 is 360, the volume of the new cylinder is 360 pi centimeters cubed. Done. Let's keep on chugging along. And we're presented with a bit of an issue here. We're asked to find the volume of a cinder block, which, when you look at a cinder block, from one side it kind of looks like a prism. But there's a problem. A cinder block has these square-ish, sometimes rectangular, holes that go right through it. Unfortunately, this means our standard formula of base times height is a little trickier to use, because our base is not just a solid rectangle. But the idea behind it is still the same. The volume of any prism is base times height. It's just that this time our base looks like this. We have our cinder block here with these rectangles that cut through it. Our goal is going to be to first find the area of this space, then multiply it by our height of 0.66. So how do we do that? Well, the area of our base in this case looks to be the area of the rectangle with these two sections cut out of it. I want to draw X's over them to show that they're cut out. Since there are two of these portions, the area of our base is the area of the rectangle minus two of these cut out portions. We're just finding multiple areas and combining them. So, what's the area of the rectangle? Well, the area of the rectangle is just base times height of the rectangle. The base of this rectangle is 1.31. The height of this rectangle is 0.66. So, the area of our base is going to equal 1.31 times 0.66 minus 2 times the area of these cut-out portions. The side of the cut-out portion is 0.33, and the length is 0.39, so it's 2 times 0.33 times 0.39. What we're doing is finding the area of the rectangle and then subtracting the areas that we have cut out from the cinder block. Let's see what we get. We end up getting 1.31 times 0.66 minus 2 times 33 times 0.39. Boom! The area of our base is 0.6072. So B equals 0.6072. That means the volume of our cinder block is just this times the height. The base is 0.6072. The height is 0.66. We're literally just taking this number and multiplying by the height. The volume of our prism is 0.400752 feet cubed. Or about 0.4, realistically would be fine. Very nice. We've got one more problem to do, and then we are done with 11.5. Now, this actually is a true story about me from high school. In high school, I was in symphony orchestra. I played the viola. And we played this song called The Hebrides. Well, I was interested because I really liked the song, and so I looked up what the Hebrides were. And it's a location in Scotland. In the Hebrides, there is a cave called Fingal's Cave, where this song is based off of. It's so beautiful because in Fingal's Cave, there are these rocks that form into hexagonal prisms. The rock is called basalt, and basalt forms hexagons when we're looking at geology. One such column is pictured here, and we have to find the volume of this column. So, we know that the volume of any prism is just base times height. It's the finding of the base that's the tough part, right? So let's see what we can do. My recommendation is, when finding the base, drawing out the base is a great way to examine it more closely. In this case, it's a hexagonal prism. Our base is a hexagon. And it looks like we're given a side measure of 8. How do we find the area of this? Well, some of you may know, we learned this in the last section. In 11.3, we learned exactly how to find the area of any regular polygon. Let's see if we can recall how to do it. I want you to pause the video here to see what you can do, and afterwards I'll talk through the problem. So pause here and see if you can find the area of this base. Let's get started. To find the area of a regular shape, remember that we can essentially split our shape into triangles. With one of these triangles, we are going to make a split down the middle. And what that'll give us is a right triangle, like so. So our goal is going to be to use a right triangle to solve the area. The formula for the area of a hexagon is 1/2 AP. So we need A, our apothem, and we need P, our perimeter. The perimeter is going to be easy enough to find. I mean, after all, the perimeter of this shape is just made up of all the side lengths. And since the base is 8, this 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 is 8. The perimeter is just the side length times the number of sides. In this case, 6 times 8, which we know gives us 48. The problem is this apothem. Since our right triangle is half of this bigger triangle, we know the base is going to be half the side length. The side length is 8, this base is 4. Now we have to find the central angles. The central angle, as a reminder, is the angle of one of these big triangles. The central angle is always 360 divided by the number of sides. In this case, 6, so it'll be 60 degrees. But we don't want the full angle because our triangle covers half of the original triangle. We will use 30 degrees. And what you may have already noticed is this triangle is a 30, 60, 90 right triangle. With any 30, 60, 90 right triangle, as we learned all the way back in Unit 9, if the short side is 4, the hypotenuse is 2 times 4, so the hypotenuse would be 8 if we wanted to use that. But our apothem here, the long side, is the short side times the square root of 3. In this problem, our apothem is 4 root 3. You could use trigonometry to solve this. In fact, if you were solving this trigonometrically, you may have set up, for instance, the tangent of 30 equals 4 over a, and then found out that a is 4 divided by the tangent of 30. 4 divided by the tangent of 30 is the same as 4 root 3. You'll get the same answer. So this is our base, b. All we have to do is plug it into our formula. Volume equals base times height. Our base is 1/2 4 root 3 times 48, and the height of this basalt column is 32. So this is what we are plugging into our calculator. I like to do it all in one go so I don't have to worry about rounding errors. 1/2 of 4 root 3, whoops, got my parentheses all mixed up, I apologize there. 4 root 3 times 48 times 32 gives us the volume of this basalt column. The volume is approximately 5,320.86 cubic inches. And we are done. Thank you so much for listening today, everybody. I hope you have a fantastic rest of your day.